Well, thank you for having me, SC and Stephen. I definitely appreciate being invited. So this is joint work with Ian McDonough, who I believe is on the call. Former student of mine. He got tenure last year at UNLV, so I'm very proud of him. Very good guy. As an aside, he has an interesting claim of fame of he worked for Art Laffer for several years before he came to graduate school. So he's always got good stories to tell. So anyway, this is joint work that we just started doing. There's no paper yet, but there will be one soon. Thanks to some funding through the Poverty Center at UK and Jim Zeliak and stuff, but our work, and we're responsible for anything we do wrong. And so anyway, they were interested in funding projects on mobility related to food security, and so it was good timing that we were working on this anyway when this conference came up. All right. So the paper builds on some of my earlier work of late, thinking about measurement of mobility, either intragenerationally or intergenerationally. And then in this paper, we're applying it to food security, which I'll talk a little bit about since people may not be familiar with what that means. And then in particular, when the data are subject to measurement error, which is a big deal even obviously in income stuff, and it's kind of been on the periphery of some of the talks at this conference, but certainly not a main focus of the work. But it is something that even when we're looking at income mobility or occupational mobility or health or things like this, then if we're going to look at mobility, then certainly we should be worried about measurement error, especially when that measurement error can be non-classical, and it might be easy to confuse mobility with differential measurement error over time. In particular here with food security is not necessarily the exact same thing just as hunger. There is a standard way of measuring it, for better or for worse. The USDA, the Department of Agriculture, has what they call this food security module that's been used for a long time. I don't know how far back it goes, but it is nice that there's a consistent set of questions that's used to measure this. And most of the time it's based on an 18-question module. There's a shorter 6-question one that surveys sometimes use if they're pressed for time and don't want to burden subjects. But typically it's 18 questions, the majority of which apply to adults in the household. And then the last few questions are only asked if there are children in the household. And the basic idea of food security, like I said, it's more than just hunger. It's also just trying to get at in general, just stress and worry in the household that's related to food, whether or not they're worried about food running out, whether or not they have to skip meals occasionally in order to save money, things of that nature. All right. And then depending on how many yes or no answers there are to these 18 questions, then the USDA has categories that they assign households to. There are 4 categories, what they call now, they've changed the naming over the years, but the worst off category is called very low food security. And then there's low food security, then marginally food secure, and then food secure. All right. So there's very little work done on mobility when it comes to food security. That's partly why they had these call for proposals of late through this Poverty Center. But just thinking about distributional mobility in general, that I reviewed in some of the earlier work that develops the method I'm going to use in this paper. You know, the most common response is just to ignore measurement error and take the income that's reported as given. But there's a relatively large literature in labor in the US, even if we're using like IRS tax data, administrative data, that we should still, not think of that as being measured necessarily completely accurately. There's things like tax avoidance or people cheating and lying on their taxes. There's just differences maybe in people's understanding of exactly what the tax forms are asking and things like this. And so even then, we don't necessarily want to treat administrative data as necessarily correct. But even if that was the case, as Lou pointed out in his talk, sometimes some of us have to get stuck using the PSID when we don't have access to administrative data, or if we want to, look at mobility in developing countries, then you may not have access to administrative data. So we don't want that to be the only solution anyway. So what do people do in kind of the income mobility side of things when they do want to account for measurement error? Basically, if you haven't read any of these papers, they are a slog to get through. They typically rely on very complicated solutions, things that Salvador's now back on here, but they tend to be more like structural models where they incorporate measurement error into the data generating process. And then what they want to do is try and estimate these models in order to be able to back out the measurement error and then simulate data that's free of measurement error, and then construct mobility measures based on this simulated measurement error-free data. So anyway, in order to do that requires a lot of assumptions that are not even easy to just parse from the papers exactly what's being assumed. And then there's a lot of simplifying things like that measurement error is not serially correlated, or that the income process is an AR1 or something like that. Or the last one, or they have to rely on restricted data requirements, some way to actually verify people's true incomes or something like that, so you can be convinced. All right. So anyway, what are we going to do in this paper to address measurement error? We're going to build on Mansky type stuff and resort to partial identification in the context of transition matrices. So it's very much just a descriptive paper. I just want to think about our usual transition matrix, like was in Xi's talk yesterday. But the only difference is we're going to not trust the data. We're going to allow for it to be measured with error, and then see what type of bounds we can derive on the elements of the transition matrix. All right. So this is Essie, you wanted to re-give your talk from yesterday, so this is part of your talk from yesterday. So why transition matrices? Well, we don't want to aggregate up. So a nice quote from Stephen Jenkins, who's in the audience as well. I was just talking to him in the chat that I think this is the first time I've ever quoted somebody who was then in the audience. So the quote was already there, not knowing that Stephen was going to be here. But just that, starting with, like Essie was saying, starting with transition matrices is a good place to start, because we don't have to necessarily worry about aggregating. All right. And they're also easily understood. So if we want to communicate the results, things like conditional staying probabilities are really easy to describe to policymakers and things like that. It allows us to look at mobility at different parts of the distribution. So there's not just, IgE is 0.5 and it is what it is. And also related to Essie's talk yesterday, we can think, depending on how you want to define the transition matrix, you could either think about relative or absolute mobility. So, if you have a income transition matrix that's based on quintiles or something like that, then it's relative. Somebody moves up, somebody else has to move down. If there's growth that doubles everybody's income, it's not going to change the transition matrix. But if you redefine things in an absolute sense, based on people's like real incomes or income relative to the poverty line or something like that, then it's absolute. And then in that case, growth would translate into movement within the transition matrix. So the disadvantage requires a choice of partitions. What's the size of the transition matrix? And then that's particularly relevant for thinking about misclassification, because the extent of how many people are misclassified within the transition matrix is not necessarily independent of the size of the matrix. If it's a 2x2 poverty transition matrix, then there might be a different fraction of the sample that's misclassified than if you have, based on quintiles or deciles or something like that. All right. The other kind of disadvantage is just, a single number is nice. So as much as we don't like to aggregate, referees in particular, and even in terms of writing up results, it's a lot easier to write a paper when it's just, hey, the answer is 0.5, and now we can move on with our lives. And by the way, people can interrupt me too, if there's any questions. So why do we worry about measurement error? People in the food security literature are worried about measurement error in food security. So it is something that literature, at least some people within that literature, are worried about. The main source of measurement error is just we're worried about people in their self-reports when they answer the questions on this food security module, whether it's because of stigma, whether it's because these are recall questions and that introduces measurement error, whatever it might be. People might have different kind of standards, reference points when they're answering these questions. So all these things kind of go into thinking about measurement error in people's self-responses to these questions. So just to give, again, a flavor of the module, I picked out the first question from the module, and it's asking about stress related to running out of food. And then an affirmative response for this question would be if you checked one of the first two boxes, that it's either often true or sometimes true. All right. And so then your overall status depends on the number of affirmative responses out of these 18 questions. All right. And so the main source, like I said, is misreporting that we're worried about, but we're also, there's also discussion on just whether or not this food security module is a good tool to measure food security anyway, since the concept of food security is this kind of vague, latent notion. And so that's a little bit harder to think about, like what that type of measurement error would do to the analysis, but you could also think about that floating around in the background as well. All right. So why partial identification? So I have a previous paper that's now, should be 2020, that's forthcoming at JBES with two other of my former students, where we developed this approach to partially identify transition matrices. And then the three of us have a follow-up paper that's currently under review that's just an applied paper looking at mobility in India. And that paper adds a few new assumptions to see what their identifying power is in terms of tightening the bounds that we didn't consider in the first paper. All right. So we're going to derive sharp bounds on transition probabilities under minimal assumptions on the measurement error process, and then we're going to consider further bounds and see what effect they have on the measurement on the width of the bounds. And this is actually Dilbert, I think, from this week. Actually, I'm working on a small little paper with Mansky, and he emailed this to our group this week. He found this on Dilbert, and he was thrilled that Dilbert is talking essentially about partial identification. All right, so advantages to partial identification, like in contrast, like I was mentioning, these previous papers that kind of use more structural approaches to deal with measurement error when looking at mobility. The assumptions here are extremely transparent, I think, and more to the point, they're easy enough to either impose or not impose, depending on your particular application and whether or not you believe that particular assumption or not. So it's really easy to present bounds under alternative sets of assumptions, and then you can, it's kind of like a menu, and you can pick and choose the bounds that you believe. And then also, like Essie was talking about, there are some scalar mobility measures that are derived directly from the transition matrix. And so then our bounds could extend to deriving bounds on those aggregate measures as well. It only requires data at 2 points in time. The only reason I point that out is, again, some of these structural models, and she was kind of alluding to this yesterday. Sometimes we have these models where you need like 5 generations worth in order to estimate a transition. Think about the transition between 2 points in time. And so here that's not going on. We just need the data at 2 points in time, and then we can plug and go. And I have code and data. If anybody wants it, you can feel free to shoot me an email, and it's all generically done. The disadvantage, obviously, lack of point identification. All right. So preview what we're going to find. Given the way we introduce and allow for measurement error in the data.
Sorry, Dan,
yeah.
Talking about disadvantages just very quickly. How easy it is going to be to do inference? Because I mean, sometimes in these partial identification models, the inference is a letter that starts with B.
Yeah, and that's kind of over my head. It was a little bit of a sticking point in our first paper. I mean, what we're going to do in this paper and what we did in our earlier work was just use this Imbens and Mansky 2004 econometric approach. We're going to combine it with subsampling, since we're estimating probabilities and we run up to constraints on the edge of the parameter space. And so my limited knowledge is sometimes subsampling does better in those situations. So that's what we're doing. Certainly there's all this work on intersection bounds and all this, work by other people on all this kind of inference and partial identification. I tried to read this literature, and basically I couldn't make it anyway. It was over my head. So there might be better ways of doing it. I haven't done it, and I don't know. the kind of straightforward, like Chernozhukov stuff on these intersection bounds, like I couldn't see how they would fit in what we're doing. I think what we're doing ends up being a little bit more complicated, and then it wasn't transparent to me on how to use that in this approach. The other thing I will say, I'm kind of not a, anyway, my personal, I don't like thinking about inference too much. Other people love thinking about inference. But in the little bit I've seen with doing inference and like using the approaches that we use for inference, 99% of the width is the bounds itself. The inference that we do does not add much additional uncertainty on top of the bounds. So, I mean, that's not a general statement or anything that like, if we really could figure out how to do it, necessarily correctly, then maybe it would add a lot of uncertainty. But anyway, that's kind of my long-winded answer on inference at this point. Okay. If after going through this, you have better suggestions, I'm happy to rethink, but Imbins and Mansky is what we do. The other applied people who do a lot of partial identification are this guy, Brent Kreider, and then John Pepper, who is Mansky's student, and then their co-authors. They still do Imbins and Mansky in all of their papers. So there might be a little bit of disconnect right now between kind of the applied partial ID people and then what the theory people are working on. And that's kind of, where it's at right now. All right, so anyway, measurement error is gonna certainly limit what we can learn. On the one hand, then to make, you might like throw up your hands and say, well, then whatever, we don't learn much. But then also we need to realize that that is a result in and of itself, that even small amounts of measurement error can really limit what we can learn. And so then what that tells me is, other applied researchers, shouldn't just dismiss thinking about measurement error because they're like, hey, there's probably a little bit, but it's small, so I'm just not going to worry about it. So the fact that things really can be sensitive to even small amounts of measurement error is a result that people should, in my view, be aware of and take note of, and that they shouldn't blow off thinking about measurement error in their own work. But we can impose different assumptions that can significantly tighten the bounds. And so that's the beauty of partial ID, is it just makes it clear exactly, hey, you want to impose this, then we can learn a lot. You don't want to impose it, then this is all we can say. We do look for heterogeneity, like a lot of the other people have been talking about. Even with measurement error, we can say some things that are not surprising, but I mean, again, allowing for measurement error, we can still say these things. For example, we can say that white households are much more likely to have a much higher conditional staying probability of remaining food secure than non-white households, and same thing for better educated households. And then we also look for heterogeneity across states on the basis of SNAP participation in this state. So here, I won't spend a lot of time on it in the results, but just we're not measuring SNAP participation at the individual household level, whether or not the household participates in SNAP. We just divide the sample into states by the fraction of the SNAP eligible population that actually participates in SNAP. And so just compare high participation states to low participation states. And there we don't find very much. All right, so jumping into the method. So we all know what transition matrices are, but just going through it. So Y star IT, that's our true outcome for household I in period T. And the periods are 0 and 1. So 0 here with intergenerational is going to be the adult, the parents. And then when T is equal to 1, that's the adult child measured at a future date and time. And then YIT is the observed food security status of household I in period T. And we're interested in our transition matrix. It's going to be a 3x3 transition matrix where the 3 states are very low food secure, and then I'm going to pool together the marginal food secure and the food secure together, mainly because my code right now is only equipped to handle 3x3 transition matrices. So anyway, just in terms of notation, I'm defining the elements of the transition matrix like she did yesterday. They're the conditional probabilities along each row. So these are the probabilities that the child eventually is in state L, given that their parents were in state K. And that's the joint probability divided by the marginal. All right. And so what we're worried here about is misclassification error. We're really worried about whether or not we observe a given household in the wrong cell of the transition matrix. And that's definitely more important in terms of like if this is applied to income, because you can have, there's a difference potentially between measurement error and misclassification in that people may mismeasure their income a little bit, but it only matters here if it screws you up and puts them in a different cell in the transition matrix than the one that they actually belong to. So like if you're estimating a poverty transition matrix, I don't care if rich people, underreport their income a little bit, as long as they don't underreport so much that it makes them appear to be in poverty when they're not. All right. So anyway, we have misclassification error as long as we see some people that are in the wrong cell of the transition matrix than they should be. And our objective is just to say what we can say about these conditional probabilities. All right. So to do that, the first thing we have to introduce is these misclassification probabilities. The notation gets a little bad. You're not gonna have to worry about it. For this audience, you probably don't care about notation anyway. Everybody can follow along. But we have these thetas that are misclassification probabilities. Obviously, it's much easier, much more natural to think about misclassification as a conditional probability. What's the probability that I'm really in this particular cell, but somehow I misreport and I show up in a different cell? So we tend to think about misclassification conditionally. In terms of working out the math for the bounds, it's much easier to work with misclassification probabilities that are joint probabilities. So these thetas are the probability that a parent-child combination is really in cell KL, but in the data we observe them in K prime, L prime. All right. So the subscript KL is the true partition, the superscript is the observed partition, and then if the subscript and the superscript are equal to each other, then that's the probability of being correctly classified. All right, so now we need to work with the bound to get the bound. So anyway, P star is what we're after. That's this. And so really simple logic, we just think about false positives and false negatives. So looking at the numerator, what we're interested in is this joint probability that a parent-child pair really is in cell KL. And that's equal to the observed probability of seeing a parent-child combination in cell KL. Plus then we have to add in all the false negatives, all those who really are in KL, but are misclassified into some other cell of the transition matrix. So this is adding false negatives, and then we have to similarly subtract false positives, anybody who's observed in KL, but who really is somewhere else. And then same thing with the denominator, false positives minus false negatives. And so those terms in brackets are just functions of a bunch of those thetas that were on the previous slide. All right. Fortunately, we don't have to think too much about the individual thetas, so I can just rewrite this as these terms, and I'm going to call this thing RKL, the denominator thing is just PK, and then these four terms in brackets, Q1, 2, 3, and 4. So RKL and then PK, the main thing there is just data. That's just the summary statistics. This is just the proportion of my sample that's in KL. This is the proportion of the parent generation that's in cell K. Right? And then it's the Qs that I don't know. All right. So I just want to work and think about, given that I don't know these Qs, I want to derive bounds on P star. All right. And I can derive those bounds by making some assumptions on the degree and the nature of misclassification, and that'll put bounds on these Qs, and that'll give me bounds. And then I can also think about assumptions that I might entertain on the P stars themselves and see if I can use those sort of assumptions to further tighten the bounds. And like I said, importantly, none of the assumptions have to be imposed. You can take it or leave it. All right. All right, so anyway, the assumptions, I'm not going to go through any of the sort of the proofs or what the bounds are, but just to tell you what are the assumptions that we consider. There's certainly others, if you have other ideas for things that I can think about and add, then that's all good. So the main assumption we start off with, again, from Mansky's work and then Kreider and Pepper in their work, is just to set an upper limit on how much misclassification there is. So the Q here is just the sum of all those thetas, all those misclassification probabilities. So the way to interpret it is just like, if I set Q equal to 0.2, then that means that I'm allowing for the fact that 20% of the sample is observed in the wrong cell than what they really are, all right? And it's arbitrary to the extent that I'm not saying who that 20% is. I'm just saying, hey, there's 20%, at most 20% of the observations in the data set are misclassified, and it could be any 20%. All right. In practice, I really have no idea what Q is. So the graphs, like I'm going to show you, we just vary Q. And at least then we can learn about how sensitive the bounds are as we allow for more and more measurement error in the data. All right. So then one assumption we can consider here where we have an absolute measure of mobility rather than relative is because mobility is not zero sum. We could think about adding an assumption that says that the measurement error is strictly unidirectional, meaning we might be willing to invoke the assumption that, hey, if people are going to misreport their food security status, they're only going to overstate and say, hey, we're doing fine, when really we're not. All right. This is going to rule out people misreporting and saying they're food insecure when they're not. All right. That seems like a reasonable assumption in this context. In the income context, it's not quite so straightforward because there is measurement error there, tends to be mean reverting. And so rich people do tend to understate their income. And so then this assumption might go away. But for food security, we think it might be reasonable. The other two that do have a tremendous amount of identifying power, we call temporal independence and then invariance. So the independence just means that the probability of the parent generation misreporting is independent of the adult children misreporting. And that may or may not be reasonable. I mean, in our data, the parents and the children are being measured at roughly 15 to 20 years apart. But again, there could be a genetic component. There could be, stigma might be passed from parents to kids. So it's not obvious that this assumption has to hold, but it does have a lot of identifying power. And then if we're willing to assume that, then we can go even further and add an invariance assumption that also says not only are they independent, but let's say the probability of misreporting that you're food secure when you're really low food secure is constant across the generations. All right. All right, so those are the assumptions we consider on the measurement error itself. They are assumptions on the extent, the direction, and the nature of those misclassification probabilities. So then we can think about additional assumptions we might be willing to assume on the elements of the transition matrix themselves. The only one I'm going to consider so far here today is just a monotone IV assumption that I'll define in a second. My code is set up, if you want it for your own work, to think about shape restrictions and then also what are called level set restrictions. The shape restriction that we have in mind here that we used when we were looking at income mobility was that you might be willing to impose a shape on the transition matrix that the elements of the diagonal, the staying probabilities, are the largest, and then the probabilities get smaller as you get further away from the diagonal. So that's what we mean by a shape restriction in this context. And then the level set restriction are restrictions that the transition probabilities might be constant across observations based on some covariate. So we can split this. We don't want to do this, but you might split the sample by race, let's say, but then be willing to assume that the transition probabilities are equal across race. So then you can tighten the bounds by looking at the intersection across the different groups. But yeah.
Yeah, quick question. So is there any way to explore the relationship between the misclassification between groups? So if the negative positive for one group, probably it's going to be related to false negative for other groups?
So that's where it gets into whether or not it's relative, whether or not things are zero sum or not. Clearly, like if you're doing income mobility and your transition matrix is quintiles, yeah, then if one person over-reports, then it's got to push somebody else down, and then that person ends up being also misclassified in the downward direction. So even though the second household may have told the truth in their response, they still end up being misclassified in the transition matrix. We're not worried about that in this case because here we're using an absolute measure. And so if a household overstates their food security status, it doesn't affect anybody else in the sample.
I have about 5 more minutes.
Low. Okay, I will go fast. All right, so anyway, the monotone IV assumption is just an assumption that the P stars are weakly increasing in some covariate. So we're going to use the household income of the parents' generation. And it's just an assumption that says, hey, if you come from a richer household versus a poorer household, then you're more likely to move up and be food secure. All right. So it imposes these inequality constraints on the true P stars, and that can further tighten the bounds. All right. I'll skip that for right now. So a little bit on the econometrics. When you're doing these sort of partial identification bounds, they can have they're biased and finite samples because they involve mins and max and stuff of the data. So again, we follow the literature and do this bootstrap bias correction that Kreider and Prepper do. And then again, related to Salvador's question, we use the Imbins and Mansky approach combined with subsampling. And yeah. So the data, we use the PSID. The parents are interviewed in 1999, and they answer the food security module in that one. And then we see their adult child when they're off in their own household. And in both 2015 and 2017, again, the PSID asked this food security module. So those are the 2 periods we have for the adult children. Anyway, I won't go into more detail than that. Like I said, the MIV is the total household income of the parents. All right. So like I said, if I could tell you that the IgE was 0.5, it would be a lot easier to go through results, but I try and make these pretty pictures, hopefully. So just to give you a flavor, so what's here, this is just for one element of the transition matrix. So this is the conditional staying probability for being very low food secure under arbitrary errors and assuming that the measurement error is unidirectional, right? And so this is the probability that the adult child is very low food secure, conditional on the parents also being very low food secure back in 1999. The x-axis here is that capital Q, the fraction of the sample that's allowed to misreport. And so when Q is 0, then that's just the observed conditional staying probability in the data, and you can see that's around 0.1. And then you can see here, even if we allow only 1% of the sample to be misclassified, the bounds already get fairly wide. And then if we allow for 5% of the sample to be misclassified, then the bounds already go to 0 to 1. All right. And the reason why that is because very small fraction are actually very low, self-report as being very low food secure in the data. So if only 3% of the sample reports being very low food secure, and you're allowing 5% of the sample to be arbitrarily misclassified, then all of a sudden we can't say anything. All right. If instead we go to the other end of the transition matrix, the conditional staying probability of being food secure, now we can say a little bit more because about 95%, 90% of the sample is in this food secure category. So the observed conditional staying probability is around 80%. And even if we allow for up to 20% of the sample to misreport, you can see the bounds still then go from 60% to 1, which is still learning something. But anyway, these sort of graphs just tell you, all right, as we allow for more and more measurement error, then how much less can we say? And since I'm running out of time, I'll skip to the next set. So this is the same thing, but now we add that temporal independence and the invariance assumptions on top of it. And so now, if you pay attention to the scale here, it doesn't go from 0 to 1. So for very low food secure, even if there were 30% of the sample that misreport, now we could still say something. The bounds are still pretty wide, but they go from 10%, let's say, to 50% or something like that. So those assumptions do add a lot of identifying power.
So then I know they represent different things, but how different would the bound be to the confidence interval I would put just using the sampling variation, just standard error? Do you know? So if I take the point estimate
The point
and
estimate,
I
but
just
put a standard error around it.
form a confidence interval,
Yeah.
how different would that?
I don't know. I don't know off the top of my head. Yeah, I'd have to look. But I mean, yeah. Anyway, just in the interest, I don't know. So this is again then looking at the conditional staying probability being food secure under this stronger set of assumptions, and you can see here just looking at the range that again these bounds are pretty narrow. They only have a width of about 4 percentage points or something like that. All right. So at the upper end, we can definitely say a lot. So then we split the sample and look at different dimensions. So just to show you one, like again, this is the conditional staying probability of being food secure. And now we're breaking it up by race. And so these darker ones up here are the conditional staying probability bounds for white households. And then these are for non-white households. So there's no formal test here, but just the bounds don't overlap is all I am doing to say that, hey, these things are different. So even allowing for quite a bit of measurement error, then we can still say that these things don't overlap. And so the staying probability is much higher for white households than it is for non-white households. If we break it up by education, again, we see similar things. At the lower end, we can't say anything that the bounds overlap. And then when we break it up by high snap states and low snap states, it looks like you can say something, but it's actually not what you think you can say. It actually looks like the reverse, that if anything, there's more mobility in the low snap states, I think, than the high snap state. I can't remember. Yeah, the high snap states actually have more, have a higher staying probability, even in the low end of the distribution. So anyway, there's not a lot there at the snap level, but even then it's not causal or anything. I mean, we're just splitting the sample, so there's nothing, I wouldn't want to make causal statements based on that. All right, so that's it. So we're interested in measurement error. We focus on transition matrices and partially identifying those. You can apply it to lots of different things, income mobility, looking at occupational mobility, health, whatever you want to look at. If you're interested in my state of code, I'm happy to share it. And then where we're going with future work is to look at the causal effect of state policies like SNAP or state level minimum wages to then see how that affects intergenerational mobility, accounting for measurement error in mobility and the endogeneity of these state policies. And I will stop there.
Okay, terrific. Thanks so much. Some questions and comments?
So Dan, in terms of actionability of things,
Sorry, I'm just also proctoring a conference right now.
The implication is that parental food security might lead into offspring food insecurity, right?
Yeah.
This might be one of these cases where one maybe ought to just focus on the poor in terms of income levels, and then maybe map it into what's happened over this period in the U.S. in terms of food stamps, and see if that sort of offers some kind of a break, an event that allows you to look before and after, but only of the poor families. There may not be enough information in the data in terms of the middle class and above to worry about what would be the benefit of including them in trying to pass judgment in terms of what is happening to transition and other relationships for the poor who might be relevant for food security. For other countries, I can see that, it involves a much larger proportion. PSID has an oversampling of the poor, right? So it's one of the better data sources for this kind of thing. But I know for multi-generational, they're all challenged. So
Yeah, I mean, so certainly we could restrict the sample based on income to look at lower income. I mean, to some extent, I would want to be a little bit careful, because one of the things that we're interested in potentially is downward mobility. So I don't know, it's kind of a little bit of a question on whose income, the parent's income or the kid's income, you're trying to restrict to being wealthy. And then we want to know, all right, maybe if you have a generous food stamp policy, does that prevent somebody whose parents were food secure, but then prevents the kids from ending up food insecure? So anyway, there's always this. Yeah, I think that probably the broader point is just that might, given our first pass at thinking about incorporating SNAP into the transition matrix, that you're limited in what you're going to find, because for the majority of people, the food stamp program is not relevant to their lives. But anyway.
I have one comment. I think your measure depends on the assumption that all the measurement errors are independent of each other, right? Because I was thinking about the copula measure we discussed earlier. Say if one person's income percentile is misclassified, that will affect the reshuffling of the whole distribution. So it means that everyone else, their ranks will also be affected by just a single person's misreported income. So in this case, I just assume.
So that's definitely right. Again, that goes back to, if it's a relative transition matrix, then somebody being one person misreporting is going to affect other people's misreporting status or misclassification status. I don't think it doesn't operate the same way here, in that, like, we're not running a regression or anything, so it's not like I have some independence assumption in the error term or something like that, where then we need to worry about it. It does relate to, sort of those thetas that, like, if one theta, if somebody moves up, then one of those other thetas must also be non-zero. And so it kind of does, you do have to think about it in terms of, all right, if I want to assume, that Q can be at least 20%, like, how does that affect the maximum and minimum values that those Q1, Q2, Q3, and Q4 elements can take on? So it needs to be kind of internally consistent in that way. And that's what you're getting at. And that's in there.
Terrific. Thanks so much.